Dear students, Assalamu alaikum. In this part of our course, we are discussing the implementation of the object-oriented feature using the Oracle, which is an object relational DBMS. Currently, we are discussing the implementation of a very common and well-known feature of the object-oriented databases, which is composition and aggregation. And basically, these two are the types of containment relationship between different classes. And as we have discussed before, that this is the situation that basically leads us towards a complex object, where one object is contained within another object. And we have already discussed that composition is one type of containment and aggregation is another one. And composition is a stronger form of containment. The book that we are following for the implementation of the object-oriented feature in Oracle, this book has not used the term composition. Rather, it has used different types of aggregations. So, basically, when we are talking about different types of aggregation, one of them is basically the composition. So, I'll be telling you about that. So, first of all, the type of aggregation that we are discussing is called existence-dependent aggregation. So, this book calls it existence-dependent aggregation that we have been discussing as the composition. So, following the terminology of this book, we'll call it existence-dependent aggregation. So, it has further defined two types of existence-dependent aggregation. One is non-exclusive and one is exclusive. When we say non-exclusive, it is that type of existence-dependent aggregation where the contained object can belong to multiple containing objects. As we have discussed before that, in the case of complex object, one object is basically the contained object that resides inside another object, which is called containing object. When we say non-exclusive, that means that the contained object can belong to more than one containing objects. And example can be like, if we can say that one employee belongs to multiple departments. So, obviously, most of the time we see that an employee belongs to one department, but as I told you that such rules, they may vary from system to system. So, in one particular organization, one employee can belong to multiple departments. So, in this case, a department object contains an employee. So, we say that one employee is contained within a department object, and the same employee can belong to another department. So, it means that one employee object is contained in two different department objects. So, this is called non-exclusive existence-dependent aggregation. We will see the implementation of this thing using the relational methodology or original relational approach. As we discussed before, that the technique that is used for this purpose is the cluster. Cluster, as I told you before, that it is a physical storage where the data that may belong to multiple objects is put together, basically for the sake of efficiency in accessing the data. So, the concept of cluster is used here. So, as you can see on your screen, you have there the statements to create a cluster. Here, first of all, you see create cluster, and the name of the cluster is department cluster. You can give it any name, and then you define an attribute, and you can call the key of the cluster as, let's say, in this case, department ID is Vasha23. We do not use this attribute as such, but this is required for the creation and the usage of the cluster. So, we have to define this attribute in the cluster. Next, you see a table has been defined, and this table is basically the department table. we define different attributes in the department, then we declare the primary key, and then we also related this table that we are defining here with the cluster. And as you can see that at the end of the definition of the table, there is the name of the cluster given, and in the brackets you have given the department ID, the attributes that has been defined in the cluster. So far what you have done, you defined the cluster, one, and secondly, you defined a table. And this is basically the table that represents the containing objects. Okay. After this, we define the employee table. This is the table whose object will be contained within the department object. So we defined the table, and as you can see on the slide in front of you, that we are defining the key of this table, that is of employee, as a composite key. And as you can see that the department ID and the employee ID, both of these, they are combined together. And basically, if you see the department ID, this has also been declared in the cluster as well. So we can relate it with the cluster, and we can say the attribute or the key defined in the cluster plus the attribute defined within this table, the contained table, which is basically the employee ID. These two jointly form the key of this contained object table, the table that is being basically created for the contained objects. Okay, then you define the remaining attributes of this table, that is of employee, and at the end you define the primary key of this table, which is a composite key, and it comprises the department ID, which is basically defined in the department as well as the cluster key. So both of them use this department ID, and the key of the employee also contains the employee ID. And then also you define the department ID as a foreign key, so that you can only create the employee object that belongs to a particular department. At the end, you relate this table also with the cluster. So what you have done, you have defined cluster, one. Secondly, you define the containing object table, and thirdly, you define the contained object table. And important thing to note is that the primary key of the contained object is a composite key that comprises the key from the containing table plus the attribute from this table. So this is the thing. And final thing is that you create an index on the cluster, and as you can see, there's a statement that says create index, department cluster index. This is the name of the index on, and then you gave the name of the cluster. So these are the steps that you perform to implement the non-exclusive existence dependent aggregation using the original relational features. So far, there is no feature that has been used which is, you can call, the additional or new feature in the Oracle. So why we call it a non-exclusive aggregation? First thing is that it is existence dependent. It means that the employee object cannot exist without being linked with an object of the department, one thing. And secondly, if you delete a department object, then all the employees objects that are contained within this department, all of them will be deleted. So these are the two things. And thirdly, when we declare the primary key of the employee as a composite key, so that gives it this feature that an object of the employee can belong to multiple departments. Or, for example, let's say we say there's an employee, let's say the ID of the employee is E101. So although the ID of the employee is the E101, but when we want to store this object in the employee table, we also have to give the ID of the department as part of the primary key. It means that E101, and let's say if this employee works in department, let's say D502. So the primary key for this object will be D502, which is department ID, and E101, which is the employee ID. So these two combined will represent the primary key of the object employee in this department, which is D502. Now, if we want to include, we can say, the same object into another department, we can do that. Why? Because E101 is, although the key of is the key of the employee, but this is not the only attribute that is included in the key, because it also contains the department ID. So it means that if we want to include the same employee in another department, what we will do, we'll create another object, and let's say department is 602. So what we can do is that we create another instance of this object, or we can say we will create another object, and the primary key for that object will be D602 and E101. So in this way, what happens is that the same employee is linked with or is included in multiple departments. Now, if we delete a department, because we have given this on delete cascade in the definition of the employee. So if we delete an object in the department, so let's say in the example that we are discussing, if we delete the department D502, so E101 was a part of the D502. When we delete D502, the object E101 will be deleted, but that deletion will be only as a part of the department D502. If this object, the employee 101, it was contained within another department, that existence of this employee will still be intact. That means this employee will still be a part of another department. And this is the situation that we call is that it is a non-exclusive and existence-dependent aggregation. If the contained object is deleted, the containing object is deleted, the contained objects are also deleted, but since it is non-exclusive, the contained object, if it was the part of another containing object, it will still be intact there. It will still be there. So this is how we implement the non-exclusive existence-dependent aggregation. The second type is exclusive existence-dependent aggregation. It means that the aggregation is existence-dependent. That means that the contained object will be deleted if the containing object is deleted. Plus, this is exclusive. Exclusive means that an object that is contained within a containing object, it will belong to only one containing object. And like previous situation, one contained object cannot belong to multiple containing objects. That is why it is called exclusive existence-dependent aggregation. So how we will implement it using the relational features? Now you can see on the slide in front of you that we'll adopt the same approach. That is, we define a cluster, and just to keep the difference, we have just minutely or minorly changed the name of the cluster. So we define the cluster, and then we define an attribute within the cluster as before. Then we define the department table that we are using as the containing object. And as before, we also related this table with the cluster. And then we define the contained object table, the table that will store the contained object. Now it is just like before, but with the difference that this time we are not defining the key of contained object as a composite key. That is, this time we are not including the key of the cluster, or you can say the containing object, as a part of the key of the containing object. This time, as you can see on the slide in front of you, that the primary key of the employee table is only the employee ID, and not the department ID is included here. So the effect of this activity is that the employee ID obviously is the primary key, so it cannot be repeated, it cannot be duplicated. So what happens is that you can enter the record of an employee just once. Why? Because the primary key is only the employee ID. And at the same time, what you did, that you declared the foreign key and linked it with the employee table. And on top of that, you will also have to declare the department ID as the not null, because as we know that the foreign key by definition can have the null value. But in this case, because this is existence dependent, it means that the contained objects cannot exist without being linked with an object of the containing object. So it means that if we declare this employee ID, which I have defined as the foreign key, as the not null, then obviously you will not be able to enter an object of type employee unless you do not link it with an object of the department. So declaring it as the not null foreign key makes it existence dependent, one. Secondly, by including it within the cluster, puts them physically together. Thirdly, when you include on delete cascade, that gives the effect that when you delete the containing object, all the objects that are contained within that object are also deleted. So this is how you implement the exclusive existence dependent aggregation using the original relational features. Now we will see how to implement this thing, the same thing, using the enhanced feature that have been introduced or included in the Oracle to support the object orientation. For this purpose, we will use the nested table feature. As we know that this is a feature that has been included as an extension in the Oracle or relational DBMSs, because we know that the original relation proposal, it just mentions that one row can have an atomic value. But when you say a nested table, then one row contains an entire table. So this is basically a deviation from the original definition. So, but this is an enhanced feature. So what we'll do, we will use the nested table feature to implement this existence dependent aggregation that we can also call the composition. So what happens there is that in this case, we take the example of the person and the course. What we do, we define a course object or course table or course class, you can say, and we define then the lecturer or teacher as a nested table inside the course. So the idea is that a course can contain multiple lectures. We can say that if we say that one course is taught by multiple lecturers, so we implement this scenario as a nested table in such a way that we define a course table that can store a course object, and inside that in that particular object we define a nested table of employee that represents a lecturer. So if one course is taught by multiple lecturers, we say that one object of the course, it will contain multiple objects of the lecturer. So in this way we can implement this scenario that we call the aggregation or existence dependent aggregation. For this purpose, as you can see on your screen, that first of all we define a type person, and as you can see, when we are using the type feature, it means that we are using the enhanced feature of the relational DBMS. So what we did, we define a type person, and we say that create or replace type person as object, and then we give different attributes of the person, and then we define this type. And what we do then is that we define a table type. We define a table type against this type. So why we are doing this? Because we have to store this type inside another table. We want to use it as a nested table. So that is why we create a table type against this type that we define the person. So what we say create or replace type person. For example, we say as table of, and then we give the name of the type that we have defined. So what we did here, that we defined a table type for the person. Then we define the course. We define the table course, in which we define different attributes of the course, its ID and other things. And then inside this table course, we define an attribute lecturer, and we give it the type person that we have given the type that we have defined. And then we say nested table lecturer, that we are saying that the lecturer will be stored as nested table, store as, and then we gave the name of the table in which this will be stored, that is the nested table. So what we have done here is that we defined a type for which we want to create the nested table, and that was the person. And for this type, we create a table type, and that table type is used inside another table to define a nested table. So this is how we define a nested table, and as you can see, we define the course table as a nested table. It contains another table inside it. Now, how will we enter data inside this table? This is shown on the screen now. There is an insert statement for the course table. How we do that? We say insert into course 3. This is the name of the table, values. Then we give the simple or single values of the course table. For example, in this case, we say course ID, which is C101. And then there's the course name, let's say, which is, in this case, database. Now, how to enter the value for the nested table? What we do for that first of all, we give the type that we have given to the lecturer while declaring it inside the course table. For example, in this case, we gave it the name person 4. Then this is the name of the type that we assign to the lecturer. Now, when we have given the person 4, inside it, we will give different rows of the table, because we have declared lecturer to be stored as a table. Now, we have said person 4, which is basically the type given to the lecturer. Now, inside it, we will give the rows to this table. So, for that, what we have to do, we have to use the constructor of the type that we created for the person. So, for each row that we want to insert into the nested table, what we will do, we will use the name of the type, in this case, which is person T, person underscore T, and in the parentheses, you gave the ID of the person and the name of the person. These two are the attributes that we defined for the contained object that has to be defined, that has to be stored inside an object. So for each row that we want to store as a nested table or inside the nested table, we will use this pattern, that basically we will be using the constructor of the type. So as you can see, we wrote person T and gave these two values for the attributes, and then that makes the one row of the inner table. Then again comma, and we use the same pattern. We gave the name of the type and then two values that will be passed to the constructor, and an object will be created that will be stored in the inner table as a row. And following the same approach, we defined another row using the same approach, that gave the name of the type and passed it two values. And this is how basically we are calling the constructor that is creating the object, and that is being stored as a row in the inner table. So this one insert statement creates one object, or you can say one row, in the containing table or containing object, one object of the containing table, and inside that object there is a further table. In this case, we have given 3 rows to the inner table, or we can say in our scenario that one course is taught by 3 lecturers. It could be any number of rows that we want to store inside, because this is being stored as a table. So there is no as such restriction on the number of rows that we can store there. So this is how we implement the existence dependent aggregation using the new features of the Oracle that are supported for the provision of the object orientation. And as you can see that because this is a nested table, so if we delete the containing object, the table that is stored inside that all table will be deleted automatically. So you can say that it is a composition. How to use this nested table? How can we access the inner table? That we will discuss later. The next type of aggregation is non-existence dependent. It means that the containing object, if it is deleted, the contained object will not be deleted. So when we want to implement this type of aggregation using the basic relational approach, then this you can see on your screen that we are taking a scenario where we say that there are different types of lab equipment that include, let's say, printer or computer or scanner or these types of things. So if we consider one computer lab, we say that there could be different types of equipment there. So if we think about a lab object comprises different objects, as I mentioned, like computer, printer, scanner, or multimeter, and like that. So if we say that we do not have a lab, or a lab is removed, that does not mean that all the equipment is gone. We say that even if we remove a lab, or if we dismantle a lab, or if we delete a lab instant or lab object, but still the objects that were contained within that lab, that basically aggregated the lab, they will still be there. So what we do, we create table for each type of object. In this case, for example, we create a table for the computer or PC, we create a table for the printer, and we create a table for the scanner. And at the same time, we also create a table for the lab. So we created these 4 tables, and we defined the attributes as we want to store the information or data about them. Then to show the aggregation means that these things are linked with each other. So what we do, we define a table named aggregate. This is the example from your book. Here what they have done, that they have included the attribute lab ID and also the part ID. Part ID means that the ID of the part that will be included in the lab. And then they also included an attribute part type. And then they introduced, or they applied, a constraint, a check on this attribute that restricts a particular part to be of either computer, printer, or scanner type. And then they defined the primary key of this aggregate table as the composite key of lab ID and the part ID. So, and at the same time, what they did, that they declared the lab ID, which is basically the part of the primary key, as well as the foreign key. So how will they implement the aggregation? For example, if we have one lab, they will include an object into the lab table that represents a lab. Then let's say we have 10 computers. So those 10 objects will be included in the computer table. Let's say we have 2 printers there. Those 2 printer objects into the printer table. Let's say we have 1 scanner, that 1 scanner object into the scanner table. So all the objects are individually at their proper place. Now to aggregate them, to represent the fact that the lab object is aggregating all these things, these links, this relationship, that each of these equipment is in the lab 1 that we basically entered in the lab table. Let's say we have got 10 computers, 2 printers, 1 scanner. So in all there are 13 equipment. To show the aggregation of all these 13 objects into the lab 1, we will have to enter 13 objects or 13 rows into the aggregate table, where each of this equipment will be linked with the lab 1. So it means that we have got 13 equipment in the appropriate tables, 1 lab object in the appropriate table, and 13 objects or 13 rows, you can say, into this aggregate. That shows that all these 13 equipment, they are in the lab 1. And this aggregate table basically implements the aggregation. See how it is non-existence dependent. If let's say we want to remove one object from, let's say, this lab, what we will do, we will simply delete the object from the aggregate. So although this equipment has been removed as being the part of the lab, but it will still be there in the original table. So it means that the existence of the contained object is not dependent on its link or containment within the containing objects. So this is how we implement the existence independent aggregation using the relational features. One thing you should note here, that when we talk about the foreign key, the foreign key in this case has been included in the aggregate table, and it goes from the lab table to the aggregate table. Another option can be that we can include the primary key of the lab in each of the tables that represent the equipment. For example, in the computer table, and in the printer table, and in the scanner table. So this is also sort of implementation of aggregation. But the difference between two is that if we do the second option, if we adopt the second option, it will become sort of an existence dependent aggregation. But if we do this way that we have just discussed, that makes it existence independent aggregation. So far we have discussed the concept of containment and its different shapes, which is one is aggregation, another is composition. Next thing that is to be discussed is the methods. The chapter 4 of this book basically focuses on this concept, but the main emphasis in the chapter 4 is that the authors want to make it clear the difference between stored procedure and the member procedure. So the focus of the 4th chapter is just to make this difference clear. So now we move to chapter number 5, which is basically the generic methods, and that chapter basically explains the usage of the methods to represent the implementation of behavior of the objects. That is basically a permanent part or a major feature of the object orientation. The chapter 5 is generic methods. Generic methods are written to access the attributes of the tables, because tables in our scenario represent classes. So we can say generic methods are written to access the members of the classes. So the approach that has been used in the generic methods is that we will store them as the member procedure. Rather than doing them as the stored procedure, we will declare them, or we will use them as the member procedures or member functions. And the idea of doing it this way is that we want to show the implementation of encapsulation, because encapsulation is a major feature again of the object orientation. The idea is that you hide the structure or implementation of the class or of the object from the end user. The end user accesses the object only through the member functions that have been defined inside the class. So this idea is basically implemented using this member procedures or member functions. So Oracle, or we can say this object relational DBMS, also gives different features that help us to implement or to enforce this encapsulation. To demonstrate or to explain generic methods, how they are defined and how they work. First of all, we define our hierarchy again, class hierarchy. This time we made it a bit simple, and we defined a superclass person as we did before. And rather than defining 3 subclasses, this time we defined only 2 subclasses. One of them is staff and other is student. As you can see on your screen, that the person class has been defined as having 2 attributes, person ID and person name. And in addition to these 2 attribute members, we have defined 2 member methods as well, and which are insert person and delete person. These methods have been included just to give the idea, just to show you the implementation strategy. Obviously, if these 2 methods can be included, we can also include other methods as well. So as the concept of object orientation is that you access or you enter the data into the object only through the methods. You do not access the attributes of the class directly. Same concept is being implemented here. You will be given, or the end user will be provided with these two methods, for example, to insert the data into the person or to delete data from the person. And obviously, as I told before, that you can define other methods as well. Then as subclasses, we have defined two classes, which are the staff and the student. Both these subclasses are inheriting from the person. So obviously all the methods or all the members of the person are in the staff and student as well. And in addition to these members, staff defines a job attribute, and again two methods which are insert staff and delete staff. The same is the case with the student, where we have defined one attribute CGPA that is associated with the student only, and then again same two methods we can call insert student and delete students. Now we want to implement these classes using the object relational features. As we discussed previously, that there are different types of inheritance that are supported in Oracle. So first of all, we are going to see how to implement these methods that we have just discussed, and to implement the union inheritance. And as we know that in the union inheritance, an object can belong to only the superclass or any of the subclasses or to the multiple subclasses. So this is the scenario. So in our example, we can say that a student can be, a particular person can be only the person. So he or she is neither staff nor the student. Or a particular person can be the student only, can be the staff only, or can be the student and staff both. First of all, we are discussing the relational approach. And see, because we are implementing it as the member methods, as the member procedures, we have to use the mix of both the relational and object orientation. Why? Because we want to store them as the member procedures. And storing them as member procedure is possible only through the type definition, which is a feature of the object orientation. So it means that we are mixing here both. We will be using the tables, but through the type. So this approach that we are adopting to represent, to store the member methods or member procedures, that is being created using the mix of both approaches, the relational and the object oriented. For this, first of all, what we will do, as you can see on your screen, first of all, we will define the type person and the table associated with it. So what we did, we are defining a type, and the naming convention that we have used is that we are saying the person underscore T. Now this T represents a type. We associate this letter to reflect the fact that here we are declaring a type. And we have also attached the letter U. This U means that we are implementing the union inheritance. So this is the naming convention, because we will be using different types of inheritance. Just to differentiate between them, we are using this naming convention. So we created a person type for the union inheritance as object, and then we defined two attributes for this type, which are person ID and person name. And then we defined two member procedures. One is member procedure insert person. This procedure will be used to insert an object into the person table that we'll create later. And as you can see that this particular procedure has got two arguments, and both are of in type because they are taking value inside the procedure only. And then we gave the signature of the second member procedure, which is the delete person. Obviously, as the name suggests, that this method will be used to delete an object from the person table. So this is how we defined our person underscore TU type. Next, we create a table for this type, against this type. and you can see the statement on your screen that create table person U. Now again the same convention, person is for the table person and U to reflect the fact that we are implementing the union inheritance. Then we say of person underscore TU, and then we only define the constraint here that PID is the primary key, and this is how we define this person table. Now this table is basically representing the class person that we just saw in our class hierarchy. After that, what we are doing, that we are defining the type body for the person, and as we have discussed before, that the objective of the type body is to define the body of the member procedures. And here you can see that we say create or replace type body person underscore TU. This is the name of the type that we just defined as. Then there is the signature of the member procedure where we gave the name of the procedure and its arguments. Then it says begin, and then there's a simple insert statement where we enter the data into the person table, and with that the insert person procedure is finished. Then we again gave the procedure delete person, which is simple and which simply gives the delete command. And the delete statement, as you can see, it says that delete from person U, this is our table, where person U dot PID is equal to self dot PID. This self is the concept taken from the object orientation, that you always call a member procedure through an object. Now this self is the object through which you have called this particular procedure. That is, you will call this delete person procedure through an object, and that object, the data of that object or all the things of that object will be available through self. So when it says person U dot PID is equal to self dot PID, it means that all the objects that are stored in the person, out of them, the one through which this procedure has been called, that should be deleted. That is why it says that the person U dot PID, all the objects in the person U table, among them the one through which this procedure has been called, that should be deleted. Next, what we do, we create the type student, and again, because we are not using purely the object orientation approach, so what we are doing is that we are saying that we define the student type as object, and we define the SID. This is the ID of the student plus the CGPA. Now we are not defining the attributes that are in the superclass table. See, although we are not using the under clause here that will inherit the attributes from the superclass, we are not using it. We are simply declaring a type student, and in this one we declare the attribute that will be used as the primary key, and secondly we have defined the particular attribute CGPA which is to be used inside the student. Okay, then again we declared two member procedures. One is the insert student and other is the delete student. This is the definition of the type. Then we created the table against this type. Here you can see that first of all we declared the SID, you can call the student ID, as the key, and secondly we declared the PID, which is the primary key of the person table, as the foreign key here. From this you can judge that we are implementing this feature, this member procedure, using the relational approach. But because I told you the concept of the member procedure is only available with the type, so that is why we have to borrow this feature from the object oriented feature, but we are not using the only the object oriented feature, rather we are using the basic features of the relational data model. That is why you see that inside the student table we have declared a foreign key which links it with the person from where it is inheriting the members. Next, here what we have done is that we have defined the type body for the member procedures of the student. Here, as you can say, the statement says create or replace type body, student TU, again the student type, and because we are doing the union inheritance, that is why U is there, as we gave the signature of the member procedure. Then we declared a local variable here. Why we have declared this local variable here, that I'll explain to you later. But see, the approach that has been used here is that we are implementing basically a situation where there is inheritance between the tables. So it means when we talk about a student, in this scenario, there are basically 3 attributes that are associated with a student. One is the ID, second is the student name, and these 2 are defined inside the person, and CGPA, that has been defined inside the student. So, but we want to give the impression that student has got all these 3 attributes, but practically what is happening, we have got 2 different tables. So it means when we are in the process of inserting an object into the student table, we will basically be entering the data into 2 tables. Part of that is going into the person table, and some part is going into the student table. So that is happening here, that in the insert of the student member procedure, what we are doing, first of all, we are entering some attributes in the person table, and the remaining attributes that are basically defined in the student table, they will be stored into the student table. So it means the user will be getting the impression that I have called one single procedure and the data is being stored in one table. But practically, because we are using the relational approach, the data is practically split into 2 different tables. We need to discuss some other technicalities of this member procedure that we'll discuss in our next lecture. For now, the Hafiz.